Welcome Professor Dr. Anthony Peirce from the University of British Columbia here today to give us a talk about modeling hydraulic fracturing using a level set method. Anthony started his career, well at least before being at UBC in 1996 he moved from McMaster University, so he has a local connection, I think, which is half the reason we have the honor of having him here today. So without further ado, Anthony.
Well, thanks very much. Thank you, Robert. Well, let's see if you're still clapping afterwards. Thank you, Robert, for your kind introduction and for inviting me to give this talk. I've been working on hydraulic fractures for more than a decade, and hopefully I can actually encourage you to see how complicated a problem it is, and maybe even inspire some of you to take up the baton and run with us. So I'm going to talk about the multi-scale processes that go on. And then with hydraulic fractures, there ends up being a free boundary problem, and it's a singular free boundary problem in that the field variables you require to know how to move the free boundary are one of them singular, and you need to calculate a distinguished limit in order to be able to establish a velocity field. So this ends up being a challenge. So I'll talk about what I call an implicit level set algorithm to resolve that. I just want to acknowledge my sort of co-workers. I'm going to be introducing work in collaboration with them. Emmanuel de Tournay from University of Minnesota, a postdoc of mine, Yegor Dontsov from UBC, and Andy Bunger, who's now at University of Pittsburgh. So just I know it's packed, but just a brief outline. I'll talk about a radial fracture and hopefully introduce you to some of the very simple scaling models that you can write down, and to show you that in fact there is multi-scale behavior that changes over time. And you can see this quite clearly from a simple high school calculation. So I find it quite cute. And it'll introduce you to some of the problems that we're going to be, the computational problem. And then I'm going to talk about what we call the MK edge of this phase space, which is really what I'm going to talk about, actually being able to model the many length scales, but on a very coarse mesh. Okay, I'll actually try and derive the governing equations, and then we'll do some simple asymptotics to be able to extract the key behavior that we want. So you need to do this asymptotic analysis, and you'll see why if you use a finite element method or finite difference, finite volume, whatever you want, and throw mesh points at it, you're not going to get the solution. And then how we can use that term asymptotics to establish this, what I call a universal asymptote, essentially to connect a viscous propagation with toughness-based propagation. So for the mathematicians, I'll try and explain what that is. And then really how one can use this type of asymptotics to derive this, what I call the level set, implicit level set method to locate the free boundary. And it gives you the tip volume, and that enables you to capture all those length scales in a sort of global weak form that enables you to capture the multi-scale asymptotics. And then I'll show you some numerical examples where we do this MK transition against the analytic solution, and then a stress jump experiments that Andy Bunger has done, which is really quite remarkable. So this K is already moved, I guess. Basically, we do a comparison with M-vertex experiments, and then when the fracture toughness is positive. Okay, so we sort of explore outside the realm that we can actually reasonably do experiments with the numerical experiments. And then I'll do some comparisons with an extended P3D model. So does anyone, are there any people who know about hydraulic fractures who've heard of an EP3D model, a P3D model? Okay, all right, so at least one person will know what a P3D model is. Anyway, I mean, this was a bit disheartening for me because I came up with this piece of code and it sort of took 2 or 3 days to calculate the solution. And then my postdoc said, well, I'll do this with a P3D model and I'll try and get the same solutions that you get, but I'll do it in 20 seconds, which I said, okay, go ahead. And he did it. So anyway, but basically you're exploiting some of the geometry to be able to deal with the simplifications. And he did some ingenious corrections. And then, I mean, you've all heard of fracking probably, and this is a situation where you want to generate multiple hydraulic fractures. And I'll just show you some of the results that we've got and some interesting sort of possibilities even for design on a simple platonic models that we've developed. It seems that you could actually, the oil industry could do a bit better than they're doing now, even save a lot of water. Okay, and then just some concluding remarks. This is the sort of conventional oil well stimulation. I mean, pre-2008, this is what everyone understood as hydraulic fractures. You've got oil in this reservoir. Typically, it's trapped between 2 sedimentary layers. And if you drilled a well bore into this reservoir and started pumping, if it wasn't pressurized, basically the oil around think of putting a straw into a sponge, the oil around the tip of the sponge would dry, I mean the tip of the straw would run dry, and then you'd have to wait for the fluid to diffuse in, and then you could pump again, but that's too slow. So they found that by over-pressurizing these, and actually what they do is they put in a packer here and a packer here, and they pump with a high pressure, they can actually generate a fracture. And the fracture being sort of clever, it searches for the minimum principal stress direction. So in this case, for this fracture, that is in this direction. So there's a stress direction in which it finds it easiest to grow in this plane. So if the minimum principal stress direction was in this direction, it would grow that way, okay, out of the board. So the hydraulic fracture we're assuming is going to be planar. And then what they do is they could propagate this a couple of 100 meters, and then they put in what they call prop, and think of it as just sand into the fracture that keeps the fracture open. Because ultimately what they want is they want then to have access to this huge surface area across which the hydrocarbons can diffuse, and then they can just pump it out. Okay, so that's basically the conventional reservoir picture. Unconventional is basically they now have the technology to drill like this horizontally, so they can drill down 2 or 3 kilometers, and then a horizontal component of this well could be 1 kilometer or 2. And then what they do is they start fracturing it from the toe to the heel, and they will try and generate these fractures because this rock is largely, it's in shales, it's largely impermeable. So they want to generate pathways for the fractures, the hydrocarbons to come into the wellbore, and then they can pump it out. So there's a keen interest in trying to model or find out ways that they can simultaneously propagate like 5 of these things at once. And then that's what's called a stage, and then they move on to another 5 and propagate those. And I'll show you how it actually ends up being quite difficult to do them simultaneously. Okay, hydraulic fractures have been going on for millions of years. This is actually in South Africa, there's a place called Tsakastad, where in fact you can see this geological formation, and here's an aerial picture of it. It's actually basically what's happened is magma's come up from underground, hit a parting plane. It gets sort of deflected, if you like. I mean, this is not magma coming from the top, but it's the same in principle. But the fracture would grow radially initially until the radius of the fracture and the length scale, which defines the distance between the fracture and the free surface, become of the same order, and then the fracture will start to move towards the softer free surface. And you get this sort of bowl-shaped structure. So basically you get these disks, which could be sort of 10 kilometers. Okay, so there was a hydraulic fracture that happened millions of years ago. Okay, so let's just look a little bit about the scalings. So now we're getting into the mathematics. I'm going to assume a radial fracture, and the radius of the fracture I'm going to assume is R. The fracture opening is, I'm going to call W, and P is the fluid pressure, if you like. So this is essentially volume balance. Q naught is the amount of fluid you pump in, meters cubed per second, times the number of seconds you've pumped. So that's the actual volume you've pumped into the fracture. And that must be matched by, I'm forgetting pi, but WR squared, just to give you, we're looking at the dimensions of things. Okay. Then we look at the active forces. This is essentially Hooke's law, that the pressure, if you pressurize the crack with a pressure delta PE, it'll open by an amount W, where this is what's called the Young's modulus. W over R has dimensions of strain. Right? So this is the elemental elasticity, if you like, of that radial fracture. Poiseuille's law, essentially rewritten in a different form. Basically, if we divide through by R, delta PM, the pressure due to viscous forces, if you like, divided by R is the pressure gradient, multiplied by W squared, divided by the viscosity, gives you the velocity due to Poiseuille's law. So that's just a statement of the viscous forces, if you like. And this is the fracture toughness. So for the mathematicians here, basically the stress ahead of a crack is singular. And by picking out the coefficient of that singularity, that's defined as the fracture stress intensity. And you match the empirical evidence has shown that if a fracture will not propagate until the stress intensity equals what a parameter called the fracture toughness. Once they equal, the fracture will propagate. Okay, so assuming essentially that they in limit equilibrium, the fracture toughness has a dimension of megapascals square root meters. So you divide by the square root of the radius, and this gives you the toughness forces, if you like. Okay, so if we balance the elastic forces and the viscous forces, so this goes fairly quickly now. You match this with this, and you write down, eliminate the velocity R over delta T, R over T. You write it in terms of the other variables. So this is something you could imagine doing. A high school student could imagine doing. You end up combining these two, eliminating the velocity. You end up with this picture. Combining these two, you can actually get the power law that the radius is going to grow with. Okay, in terms of the other parameters, the flux, the modulus, and the viscosity. Mu prime is basically 12 mu. It's a scaled viscosity. And from that, you can plug back in, you can get the power law for the width, power law for the pressure. So basically, the fracture width is going to be growing, the pressure is going to be decreasing with this power, and the radius increases with that power. So this is basically what's going to happen. And these scalings come out from the PDEs as well. It doesn't, but it's so nice to have it sort of fairly clean on the, you can do this on the back of an envelope. So if you take the odd person out here, the toughness forces, and divide by the elastic forces, which are the same as the viscous, you get a dimensionless quantity, which is the dimensionless toughness. Okay, and this, it's time dependent, and you can see that basically as t goes to 0, basically the dimensionless toughness is not important. So basically viscous stresses dominate at the beginning of the fracture's life. And ultimately, as t goes to infinity, the toughness forces become dominant. So now we'll go to the next case where we balance toughness forces with elastic forces, do the same sort of calculation. You get a different power law, different power laws, different powers. And lo and behold, if you take the odd person out, the viscous stresses, and divide by the elastic forces, if you like, you get a different power law of decay. But interestingly enough, you can see that for small times, the dimensionless viscosity is dominant, and it decays with time. Notice there that, in fact, this is related to the dimensionless toughness via this quantity, so you can actually determine the transition time. Basically, this is essentially, this thing equals some transition time squared, this quantity here. Okay, so that will tell you the time at which you'll transition from viscous to toughness. Okay, so what I'm going to do is we can think of this phase space. I mean, there's also leak-off in these fractures, but I'm going to consider the transition from viscous to toughness and look at the length scales that happen. So here's just to summarize, here's the dimensionless toughness. You can see the same quantity just reciprocated here inside the bracket. This is the dimensionless viscosity, and this is the transition time. And basically, I'm going to look at the simulation over the life of a fracture. And we will do this for a radial fracture, compare it to analytic solutions, and then we'll go and look at what happens with a stress jump, where basically within the same fracture, you can have part of the boundary being pushed forward viscosity driven and another part toughness driven. Okay. All right, so now let's get to some PDEs. I don't want to disappoint the mathematicians. They like to see a PDE. So think of a fracture, and we've got an element here. W is the fracture opening. And, this has jumped off the screen here. Well, you'll see it's a Q. Let Q be the flux in, and Q be on the other side be the flux going out. So if this is larger than that, then basically the fracture had to open for mass to be conserved. So we can quantify that area. Notice this is an area because I'm considering this per unit length in the out of plane direction. So the total change in area per unit time is equal to the flux in minus the flux out. So this is a conservation law you've seen in many contexts, traffic flow, many other contexts, fluid flow in a pipe, etc. So now what we're going to do is we're going to put in Poiseuille's flow. This is essentially a solution to the Navier-Stokes equations, assuming no slip conditions on the boundaries. You get this classic parabolic shape, which looks like this, which is governed by the gradient in the pressure. And basically, you can integrate in the y direction, and that's what gives you this 12 mu, which we call mu prime. Okay. Now you can eliminate the flux, and now you end up with this little PDE. Okay, so the complexity in this PDE is it's degenerate. W can go to and will go to 0 at the tip. So the pressure gradient can go to infinity. Okay. So, I mean, it's a little bit like a diffusion kind of equation. Anyway, so that's our conservation of mass. All right, so we've dealt with what's going on inside the fracture, the fluid flowing. Now I'm going to talk about, and this is just for the mathematicians, the civil engineers would be very familiar with this. Consider an elastic bar of length delta x. It's subjected to two stresses on either side. And basically we're setting up F equals ma. The stress times the area gives us the force on the right-hand side minus the force on the left, plus some body force, which is a force per unit volume, times the volume must be equal to rho times the volume times the acceleration. Okay, F equals ma. I mean, we're still trying to deal with Newton's laws. Okay, and you divide through by a delta x and take the limit, you get d sigma dx here, force and acceleration. And we're not going to track the acoustic waves, they've long gone. So we're going to look at this thing in quasi-equilibrium. So force equilibrium. So you combine that balance of linear momentum with Hooke's law, and everyone's probably done this experiment at high school or in first year physics. When you take a spring and you pull it, basically it extends by a certain amount on either end. That would be the change in displacement divided by delta x, which is an approximation to the derivative. This is what we call the strain, and there's a linear relationship. This is discovered by Hooke, or first reported by Hooke, I think. And if you write it in terms of displacements, or displacement gradient or velocity, those were the two forms of Hooke's law. Plug into these, we get a combined equation, and these are the equilibrium equations, okay, in 1D. Now you can see the 2D analogy. Here you can, stress is basically a tensor. Think of a 2 by 2 matrix that's symmetric, okay, and you want to find these field variables, and you can see essentially you do exactly the same process on this element, and you'll come up with these equations. Okay, and these are the equilibrium equations. Now they can be written in the equilibrium equation in tensor form like this, and the Hooke's law like this. Okay, and so what I'm going to do is I'm going to talk mainly about a boundary integral method where we'll set up a Green's function and we'll look at the propagation of the fluid in the fracture. So this would be a 2D Green's function. This would be a 2D problem. I'm going to look at planar fractures in a 3D elastic medium. But now, other methods would be the finite element method, but every time the fracture moves, you've got to remesh. So this is not so good for the finite element method. There's another method I was talking about to the grad students, the extended finite element method. Robert Gracie here is an expert in this area, and basically we've been also looking at models using the XFEM. Okay, but in my talk, I'm going to be talking about essentially those. So to set up the Green's function, we take the elastic equations. These are linear PDEs. You take the Fourier, you set up jump conditions. So what I'm going to do is I'm going to assume that I've torn the material apart in the y direction, and that the stress jump across the x-axis is 0. Okay, and we only have a jump in the y direction. You take the Fourier transform in x, it becomes an ODE in y. It gives you linear solutions. It's a linear ODE. You match the upper plane to the lower plane, and you end up with this. So you could, it's 2 pages of algebra. Okay, you end up with this. You invert the Fourier transform. It actually becomes a Laplace transform because of symmetries. You end up with this. And for the mathematicians, this is sort of an interesting thing because it tells you what we're going to write down an integral equation. This tells you what the symbol of the operator is. It tells you that when you operate with the integral operator, it's like taking a derivative because you're multiplying by the absolute value of the wave number. So it's like taking a derivative, and we'll see that. And so I've taken the limit as y goes to 0. So if you take y going to 0 in this case, all these terms drop out. You get 1 over x squared. R is x squared plus y squared. When y goes to 0, it just reduces to 1 over x squared. If y goes to 0, that goes out, this goes out, and you're just left with the modulus of k. Okay, so this is the kernel of this integral operator. So now putting this all together. So you've seen this. You know where that comes from. I'm putting fluid into the fracture. Okay, there are viscous losses here. There's also leak off. Okay, I'm not going to talk much about that. Basically, that was a 1 over x times e prime over 4 pi gives you essentially the stress at a point x away from the source. So you have this shift, a convolution, if you like. If that's the stress due to a unit tear. So if you have a tear of an amount omega, then this gives you the stress at a point x due to a unit tear at psi. You add all those up, it's a linear problem, linear elasticity, and this is sigma, PF, the fluid pressure minus some geological stress gives you the net pressure is equal to the fracture opening W. So this gives us a couple system of integral partial differential equations. Okay, so boundary conditions, you have that the fracture width of the tip should be 0. So that makes this a well-posed problem. And we're assuming that the flux of fluid out at the tips is 0. So we're not losing any fluid, leaking fluid from the tips. Okay, so what complications can we expect? Well, as W goes to 0, the PDX can go to infinity. So this is a degenerate PDE. So we can expect singular solutions. And we'll come back to that. Each of these equations is not so bad on its own. If we knew the pressure, we can get the width. If we knew what W was, we can calculate the fluid pressure. But when you put them together, and you combine the fact that you don't know where the free boundary is, this makes it a hard problem. Okay? And so if we knew what L was, then these two equations are enough to solve for the width and the pressure. However, if we don't know what L is, we need to get an extra condition, and this is known as you use the fact that the fracture opening has to have this asymptote, which is dictated by the stress intensity factor. So it propagates, the fracture has to have this shape that matches the stress intensity factor to the fracture toughness. So that's what's known as a propagation condition. It tells you basically the amount of energy that's involved to break the rock. Okay. So that's the full 2D model. And you can integrate by parts, impose the boundary condition. This becomes, instead of the previous operator was hypersingular, this now becomes a finite Hilbert transform, a Cauchy operator. But you can see you're essentially taking a derivative of W by operating with this integral operator. If you do the same process in a 2D problem with a radial fracture, you have to integrate over a surface now. You don't know where the boundary of the surface is. The lubrication equation boils down to this same idea, gradient of the pressure. This is the Green's function essentially. We've got 0 flux boundary condition, propagation condition. And this is what makes the numerics difficult to track the free boundary, because this pressure will go to infinity, a pressure gradient will go to infinity, and W will go to 0, and you get something finite. So to approximate these by polynomials is a disaster. If you want to use the finite element, finite difference, finite volume method, this is a mess. Right? You just can't catch that distinguished limit. So you've got to use the asymptotics. And that's where the sort of free boundary problem is resolved, in my opinion. Okay, you can write this down in a sort of operator form. Write this down. You can imagine even discretizing this. Let this be the operator A. If you eliminate the fluid pressure, and assuming this is a constant, say, then basically you end up with this evolution equation. So for those of you who numerical people, this is essentially a diffusion-like operator. You can see that the divergence of the gradient. That's a diffusion kind of operator. So this is going to bring, if you wanted to do Euler time stepping, okay, explicit Euler's method. So you're going to get a CFL condition that, because of this operator, it brings in a delta x squared. This one brings in another delta x. So you have a time step restriction that is delta t is less than something times delta x cubed. That's not the end of the world, but what makes it really complex is that this operator is a local operator. It's got just derivatives. This is a non-local operator. So every time you take a time step, you've got to do a full matrix multiply. So that makes your problem, you've got to do 10,000 time steps, and every time you've got to do this full matrix multiply. So it's bad news. So you've got to do implicit. So there are a whole set of tricks that you've got to do to just do that implicit time stepping. Okay, but I'm not going to be able to talk about it now. Just rescaling everything. This is essentially the same exercise. You can get 5 dimensionless groups, same sort of thing here. You take those same equations, use the chain rule essentially, you can boil it down to these. And now if you equate GM and GE and GV to 1 and set that to 0, then you get the dimensionless toughness. All of this basically goes back to that pressure balancing scaling analysis that I was talking about. I just want to show you that basically you can take that integral operator, and if you zoom into the tip, essentially as long as you've got no kinks along the boundary, you can express the integral operator in local coordinates, with xi and eta, and reduce the whole thing to essentially the plane strain case. So we can take that integral operator that's for the radial fracture or arbitrary fracture, it doesn't matter what it does, and you can boil it down to the same as that 2D thing, but from 0 to infinity. So for the mechanical or the civil engineers, think of this as if you're a flea and you're close enough to the free boundary, and you look left and right, it looks like that thing's going off to infinity. As long as you're close enough to the thing, it's going off to infinity. So if it's going off to infinity, basically you're in a state of plane strain. Okay. So that's essentially algebraically what's happened. So to capture the asymptotic behavior, we assume a power law. For the mathematicians, this is just essentially a Frobenius solution. We're looking for a power law Frobenius type solution. Plug into the elasticity operator, you get this. Simple residue calculus gives you that. Okay, so this is an interesting thing because essentially it's telling you that if you have this s to the alpha minus 1, it reproduces that. So this is an eigenfunction for that operator, and that's the eigenvalue. Okay, if you take the lubrication equation and you go to a moving coordinate system, you can rewrite it in this form where v is the velocity as a moving coordinate. Integrate once, you end up with this lubrication equation. And now if you notice that if alpha is equal to half, that vanishes. So you've got to get the solution from the balance between these two terms. If omega, cancelling one of the omegas, cancel this one with this one, you get omega squared. But omega looks like psi to the half. So that's just basically psi. Integrate and you get a log. So the lubrication equation says if you've got alpha is a half, it gives you a log singularity in the pressure. So what you can do now is balance this term with this term. If these two terms are going to balance, you basically plug everything in, with the pressure you've given by this, omega given by that, group the powers together. 4 alpha minus 2 must be equal to alpha. That gives you the solution. So basically you've got a power law, and this is what's called the viscosity dominated solution. And so that's what I'm going to do, is look at the transition in space from this to this. So if you take that semi-infinite problem and rescale everything, you can boil it down to the connection between a square root on the really fine length scale. Look at how small these 10 to the minus 7, 10 to the minus 8 when you get to the toughness condition, and that you change to a 2/3 power about order 1. So many length scales are involved. So you can solve this connection problem numerically, and here's the one asymptote. This is done numerically, and you get the next asymptote. So you can solve this, and this is what we call, this was done by Dmitry Garogash for his PhD. This is what's, we call the universal asymptote for the MK edge. So what I'm going to do is to use this solution to be able to transition from M to K, because basically you've got that. Okay, so basically you express W in terms of a sort of finite length scale, in terms of this infinite length scale, do some remapping, and you can rewrite omega for the sort of finite mapped case in terms of this universal asymptote. So this is just essentially a whole lot of manipulations with the chain rule. So you can essentially write omega in the finite case in terms of this semi-infinite solution. And the parameter that determines what's going on is the velocity field, the local velocity field. That's what selects what length scale is active. Okay, so how do you solve this thing numerically? So to solve the integral equation, I just use piecewise constant. So I express this in terms of basically a whole lot of, think of putting down squared paper where the fracture is going, you expect the fracture to go, and on each of those squares I assume that the solution is a constant. Okay. Plug in, you end up with this integral operator. I mean, it's just basic integration. And I mean, you really are getting away with murder, because at the edges of these squares, the stress is infinite, but we collocate at the midpoint. So it's a collocation method. So the stress is going off to infinity, but we still get a solution at the midpoint by only sampling at the midpoint. Standard finite volume method to discretize the lubrication equation. Basically, we integrate over a particular cell, one of those squares. You end up using the divergence theorem. You've got fluxes on the boundary, which you can essentially, because we have a regular mesh, we just calculate those fluxes by differencing. Essentially, J is calculated by pressure gradients in each direction. Put that all together. This is standard finite volume discretization of the fluid flow equation. So now to deal with the free boundary. So we know how let's assume that fracture is propagating in a toughness regime. So W is asymptotic, well, equals K prime over E prime S to the 1/2. Okay. So what I do is I say, assume that we know where assume that the fracture boundary is where it was at the previous step. Pump a bit more fluid in, get an estimate of omega, because let the fracture open. That tells us that we know if omega is given at a particular point, then we know where the free boundary is. So given omega, we can determine the free boundary. It's as simple as that. Getting psi at each of these, what I call survey points, not points that are cut by the front, but just in, okay, we apply the asymptote to determine where the free boundary is. And basically, if the fracture starts off, it's too small, you pump a bit more fluid in, the width goes up, then you move the fracture boundary out a little bit to match that width, and then you iterate until it comes to rest. And it comes to rest on the asymptote. So you get all these estimates of where the free boundary is from these points. So what we do is we use a level set equation, the iconal equation. You set the free boundary, the distance to the free boundary from some asymptote, assuming a sign convention that it's negative, and we want to find the level set where t is equal to 0. That's where the free boundary is. It's as simple as that. So you just have to solve the iconal equation, and that tells you where the free boundary is. This is a standard technique, first order method from conservation laws. Essentially, you've got to upwind so that you get the appropriate approximation. So this is standard method from solving Hamilton-Jacobi equations. Essentially, it boils down to solving a quadratic, essentially. There's a nice geometric interpretation. If you knew the distance to the free boundary at these 2 points, you can calculate tau according to this, and it's just simple geometry or trigonometry, actually. And what comes out in the wash is the distance L from the corner to the fracture front and the inclination alpha. So it gives you everything. So the idea is, if you've got a particular asymptote, you basically invert, given omega from a trial solution, you invert the asymptote to give you psi. That gives you initial conditions for the iconal equation, and you solve. This is for the k vertex. Now, I first did this one, and then I thought to myself, my goodness, I've got the velocity here. So I'm fooling myself. But what I did was I replaced the velocity with the distance, the backward difference between the current level set and the previous level set. And that gives you the velocity. Plug it in. So end up you end up solving a cubic for the viscous asymptote, and that one's trivial. Okay. For the generalized asymptote, basically, you've got this mapping, essentially, where this is a known function. So essentially, plugging in for v, you have to solve this nonlinear equation at every one of those sample points. But it's doable. You just use Newton's method. Okay, and that resolves the free boundary. Okay. So this is an idea. I mean, here's a sort of spreadsheet, if you like. These were the distances to the free boundary. I ran the iconal equation, got the actual intercepts, and this is basically locating where the free boundary is. Basically, the interesting thing is, think of this as you've got this this asymptotic behavior from here's the front, and we know it's some sort of we've got a functional form for the fracture opening back from this. So basically, what we can do is, and this, as you go down to finer length scales, we can integrate that whole function over this element. Okay, and what we do is we calculate the volume that's trapped under the surface for, I mean, even that generalized asymptote. And that's enough to capture all that fine scale behavior. Okay, I mean, it's basically, it's a simple thing. You calculate it over a triangle, assuming that it's got that particular asymptote. You use the universal asymptote. Essentially, you can write everything in terms of the 0th and first moments. And essentially, basically, you can get this polygonal region by taking the big triangle and subtracting that asymptote and that asymptote, that area and that area, if you like, or volume and that volume. And that gives you the final result. So it's a trivial second-year calculus problem. So essentially, knowing the volume of fluid that's trapped in there from the asymptote, we know what the fracture width is, and we ascribe it to be the average value. So now, what is the variable in the tip region? Well, you know what the volume, the fracture opening is. So what you do is you use volume balance to determine what the pressure must be. So the pressure becomes the primary variable in the tip. So putting this all together, you solve for the change in fracture opening in the what we call the channel regions inside the fracture, the fracture pressures, the fluid pressures in the tip, and that gives you the pressures and widths. From the pressures and widths, we invert that the asymptote, if you like, to get the distance to the free boundary. We run the iconal equation, determine where the free boundary is. We get all these quantities, and we keep iterating. It converges in about 5 iterations. So I've got a couple of minutes here. I'm going to just show you some of the transition from here to here for a radial fracture. So you'll see it starts off viscous and it goes toughness. So viscous will be magenta and toughness will be black, if you like. So it starts off, so these are just snapshots. Basically, if the dimensionless toughness is 1.25, it's very close to the viscous. If it's much larger, it's close to the toughness regime. And I basically ran a simulation where it went from there out to there, a transition from viscous to toughness regime. So it agrees very well with these extracted from a radial solution. So that was done with assuming a one-dimensional model. So this is full 2D. By putting in the correct asymptote, you get a very good match. And here's a sort of movie where basically it starts off on the viscous and moves over to the toughness regime. And you can see it's actually getting closer and closer to the toughness fracture. And you can see the toughness pressure is sort of flatter than the viscous pressure, because the viscous pressure is driven by the pressure gradient. Okay. So one of the important problems in hydraulic fracturing actually comes from this geometry, where you've got a stress barrier. So you've got a higher stress here, and a lower stress here. So what happens is the fracture starts off radial, it hits this boundary, and then it starts to go like a surfboard or a blade-like fracture. And the big question is, how much does it, the practitioners always want to know what the height growth is. How much is it going to go into the outside the reservoir layer? So this is a big problem. And this geometry is so important, they think of this as what's called the P3D geometry. They want to know what the length and the height is. Okay. So if the aspect ratio gets large, then basically you can cut this thing and assume that you're in a state of plane strain. So that gives you a special solution. Okay, so Andy Bunger at Pitt, he did a beautiful experiment where he machined the surface of the block to generate these stress jumps. He got an analytic solution, actually got one of these numerically controlled machines to put in the shape of the block and then pushed on it, and that generates a stress jump. And you can see here it starts off radial, starts to go blade-like, and you can see the blade-like behavior. So here's a comparison. This magenta box is the actual experiment, and the red is the numerics. Okay. So what I'm doing is I'm assuming I'm going to look at, away from the viscous regime, I'm going to look at a situation where you put in some toughness. So this would be gluing the surfaces of the block together, and you've got to see, you've got to actually expend energy breaking the rock. So what I've done is I've colored the length scales here to show at what length scale on this asymptote we're operating in. So along the boundary of the fracture, this determines what the length scale is. So if it's a tougher fracture, it's more in the toughness regime. So if you have a look here, I mean, this is close to the viscous regime. The red would be the viscous regime, and this is for the dimensionless toughness being 0.63. Here it's propagating in the viscous regime. Here it's propagating in the toughness regime. So it's actually transitioning from one to the other around the boundary. Okay, so if you weren't able to model all this multi-scale behavior, you'd be in deep trouble. Okay. All right. So, and that's the sort of key to determine the length scales that we're capturing. We can match Andy's experiments pretty well. That magenta is the numerics, and these red dots are the experiment. So the black curves are when I put some toughness in. So this is the story where I gave it to my postdoc. He did a plane strain solution, and you can see this is a sort of thing you can only show to consenting adults. But anyway, it's a whole lot of algebra, and you can come up with analytic solutions for the cross-section and how much the height growth should be. So this is probably a lot of conventional designs are done on this. But you can actually characterize, so these are Andy's experiments, the two red dots. These are the numerics. So you can see the classic experiment is really bad in the viscous regime, and it's not so bad for the length, but as the toughness gets large, it can't put toughness in the tip, this P3D solution. It gives you a very bad, its length is terrible, whereas the fracture length drops off with increasing toughness. So this sort of characterizes the poor behavior of the P3D fracture. So just to show you, here's the viscous solution, and this would be what the P3D model would give you. So it's quite a bit out, 50%. Okay, and if you put toughness in, that would be what the P3D model gives you, and this is what the true answer, or the numerical solution is. So it's way off. Anyway, I showed that, and these are sort of the widths and the pressures. I won't go into that. So I showed this to Jaeger, and true enough, he said, I can do better. I'm going to fix this model. So look at what he did. He can now match it to within 5%. And my code takes 2 days to calculate. His takes 20 seconds. So it's quite humiliating. But anyway, it's good. But it shows what you can do if you're doing it smarter. Right? Okay, so here's another model. Experiment where you have a stress jump, high stress, intermediate to low stress. So what's going to happen is the fracture can't go into this region. I'll just set it going. here's a movie where the fracture can't go into the upper layer, and you'll see it will stop here, and it forms this sort of muffin shape. Okay, if you like, you can sometimes see the little particles coming down of fluid. Okay, so you can see now it's sort of getting fairly well formed. There's a high stress region there, intermediate in this region, and then low stress. So it's finding it much easier to grow in this region. Okay, so we took the parameters from his experiment, and now he actually had the capacity then to actually digitize the boundary, and we looked at the snapshots against the numerical model, and it captures it pretty well. Okay, so now on to the last topic, multiple planar fractures. So this is what people are really interested in now, is to look at, and I'm not going to do much here. Now you've got the same thing in one plane, but now you've got to have coupling between the fluid flow. So here, basically, the added sort of complexity here is you don't know how much fluid to partition to each fracture. So assuming that the pressure across all the fractures is constant, you've got to solve for this as a unknown in the problem. So that's another complexity. And so there's fluid mechanical coupling through the well bore, if you like, and then there's elastic coupling through the stress tensor, the Green's function for these. So there's shear stresses and normal stresses and opening and rides. So there are three components of fracture: opening and shearing. Okay, so this is the sort of state. I've now extended that P3D kind of geometry to 5 fractures, if you like, similar pay zone. And I just wanted to show you in the toughness regime, you get the 2 outer fractures growing and the middle guys can't grow. In the viscous regime, you get you can get them to simultaneously grow, provided they're far enough apart. Okay? If they get to be close together, they start to interact and the central fractures stop growing. Okay, and this I'll show you, it gets really worse. So you can model multiple of these things. This takes a week to calculate, never mind a few days. Okay, so actually, I just wanted to go back. Andy he assumed an infinite array, and he came up with this interaction. If you basically further than this apart, h is the distance that the fractures are apart compared to the height of the pay zone. If you further apart than that, then the interaction is not going to be significant. If you're closer together than that, you're in trouble. So here you've got Z, which is all the fractures in what they call a stage. Z is about H. So these are really close together. And this is how they want to propagate them. And this is typically what happens. The 2 outer fractures grow, and they squeeze these guys. They find it difficult to grow. So these, you get a localization, and these guys are going to take all the fluid. So I said to Andy, but why don't we just move this guy closer to this one? So this one has more competition, and the same with this one, and let the middle one grow. And sure, well, okay, so this is the sort of snapshots. Have a look at the fractured area, 3424 at the end of 143 seconds. Radius, fluxes, and pressures. I assume that the pressure is constant, the same in each of the well bores. So you get a partitioning. I've numbered them red, green, blue. So the green and the blue, the ones in the middle, because it's a symmetric array, I only need to keep track of 3 of them. Red, green, blue. The red guy, the outside guy, takes everything. Okay, these are the fracture widths. So then I said to Andy, well, why don't we just move these guys closer together? And then something completely unexpected happened. Basically, these guys interfere with these and allow the middle guy to grow. And then they take over. These start competing, so it becomes more favorable for those to grow. So the actual fractured area is far greater. So I'm going to just skip these. You can see a completely different dynamic. Basically, the red guy gets shut down, and the green guy, red-green, the intermediate fracture, sort of takes over. Okay, so you get actually a squeegee effect. So those two, the fractures 2 and 4, they actually start to push the fluid, displace the fluid away from the middle to the boundary in the other fractures. Because the others are not taking any fluid, but they're still growing. Okay, so if you have an experiment where we only change one variable, I think I'm probably running short of time, but if we only change H1, and this is H1, and everything else is the same, this is in the middle, that distance is always the same. So if you only change H1, if you vary it, that's where it's uniform. This is on a 20-meter array. You get an optimum. Okay. And actually, someone asked me, well, what happens? Is it any better than a 3-fracture array? Well, a 3-fracture array, because the middle guy doesn't have competition from the others, it does grow more, but not that much more. It's still inhibited. So those interference fractures are making a difference. Actually, and I spoke to the people in the oil industry, and they say, no, but you always do it uniformly. That's the only way. But in fact, there's a whole lot of potential for optimization. So it happens with a 6-fracture array, same old, and now you can get a similar sort of picture. Okay, but I suppose this is the interesting one. If you, at 108 seconds, 3-fracture array, uniform, okay, it's almost the same as the 6-fracture array. Look at that. That number there, and that number, all the same. So basically, if you've got 3, 4, 5, 6, only the 2 outer ones are going to take fluid. They're going to steal everything. But if you fiddle them around and interfere, then you can do a whole lot better. I mean, 35% better, 68% better. And I mean, I took it out and you can get 46 or 74. So I mean, it's also robust to perturbations. You can also do sort of funny tricks. Oh, and another thing they're interested in is multiple stages. So you start with the one and then you move on to the other. So now it's a big question because there's a previous existing stage here. It shuts these guys down and only 1 fracture grows. But now we actually got a 4-dimensional space to actually try and optimize over. So yeah, I've been guessing. But anyway, I think I've spoken enough. Okay, thanks very much.
Thank you for that talk. Those who are not in the oil and gas industry, these are kind of billion-dollar type questions, potentially.
Potentially.
If they'll listen to you.
Yeah. But it could be pie in the sky too, right? So, yeah.
Not quite, I don't think. So, do we have any questions for our speaker?
Yeah.
Talking about optimization, when you optimize the area, I'm just wondering if it's possible to optimize the area and the width. Will it be possible or not? Like having the width of each fracture maximized?
Well, the thing is, the width is dictated by the mechanics. So we can't really do that. But the thing is, what we haven't modeled, and I think this is what you're getting at, is we haven't, because basically these fractures that I'm talking about are going to just shut down when I move the fluid out. I mean, just like a balloon, when you let the air out, it goes and shuts down. But what they do is they put the sand in. So that's an opportunity for optimization, right? If you put propant, but we haven't even got nearly, I mean, if I'm modeling propant, I'm in deep trouble. Because basically you get screen out, you get shocks forming at the fracture tip. As basically the propant basically backs up, just like in a traffic flow problem. You get the same shock behavior. But it's not a nice shock because it's essentially coupled to this non-local operator. So to actually write down schemes that are going to capture that shock behavior are incredibly difficult. Yeah. But I think what you're talking about is actually if you put propant, because you'd like to get the most propant squeezed in and the most surface area broken, because that's going to give you conceivably the best chances for production. So you're right. But these ones, it's not in this model because they'll just close, right? And that's dictated just by the mechanics. You know. Okay, yeah. I hope I answered your question. Yeah.
Any other questions?
But you hit on a flaw in my model because I'm not putting propant in. But it's bad enough.
But what about like increasing the pressure? Because what you said is correct, because the width is controlled by the mechanical properties of the rock. But
Yeah.
as a matter of fact, we can increase the pressure.
Oh, yes. Yeah. So you could.
Like optimization between the width
Yes.
and the pressure.
So we could, and some of the practitioners believe that you've got to just really beat this rock. You know, you've got to just pump with an extraordinarily high volume which is going to increase the pressure. And so you could play around with that too. So that you're increasing the pump rate, that'll drive the pressure way up. And then the width is going to go up, obviously. And then you'll probably get more propant through. So, but I mean, there's so many things to optimize when you put the propant in. Because the propant's going to localize, it's going to settle, right? So any of you want some complicated problems to work on, this has got everything. There's shocks, there's everything in this.
Any other questions for our speaker? I have a whole list of them, and I can't even remember them. So one of the questions I had is going back to some of those scaling laws
Yes.
that you had at the very start. I mean, one thing that companies want to know is they always add chemical additives to change the viscosity.
Okay.
Is there any point in doing this for such once the fractures get large enough? I mean, what can you use
probably
that information?
Yeah, you could use it in design. But that being said, most of the companies don't even believe in the viscous solution. So they're all designing on toughness.
I'm not even sure they're doing that because my second question was
Actually, this is becoming public. Yeah.
It's becoming quite angry.
Yeah. No, but I mean, so a lot of the companies are designing with the toughness propagation criterion. They're not using the viscous asymptote for sure.
I would say that some of the solutions they use, models they use, actually the assumption is that the toughness is 0. So the
Okay.
KN models, fracture toughness is
Yeah, in the horizontal, yeah, is 0.
So
Yeah.
what is this? So what type of mistake might
It
one be making?
It could make a huge difference, yeah, to the design. Absolutely, yeah. But without actually putting the toughness in and putting the viscosity in and looking at the scaling, you're not actually able to say one or the other, right? One is going to... And in fact, Andy Bunger did experiments where he actually managed to get the viscous solution and the toughness solution. But they had a devil of a job to get the viscous solution out. They had to take some syrup and evacuate it to get a thick enough goop to pump into the fluid, the fracture, to get it to fracture in a viscous regime, right?
Is that because of the scale of the lab experiment?
Exactly, yeah. But the scaling, they had to do all the scaling and get it right in order to get it into the right regime, right?
Yeah, that makes sense.
Yeah.
Any other questions for our speaker? Well, if there are no questions, then I think we've slightly passed our welcome here in terms of the room. So let's thank again our speaker for an excellent talk.